Okay, I guess it is now. Okay, Melody and Winner, can you tell us what you understand by stoichiometry? We have kind of did a bit introduction to this topic before now, but since you guys said we should go back to it again. Okay, stoichiometry is all about balance and also about relationships. Okay, it often is used to relate reactants and products of a particular chemical reaction or a chemical process. It is used to relate, it can even be used to relate a reactant and another reactant. So it's just telling us about proportion. It's telling us about how under balanced circumstances one thing can relate, the quantity of one thing can relate to the quantity of another that we are being given. Okay, so we have, for example, um A reacting with B to give us C and D. Okay, so stoichiometry can really tell us the relationship between A and C. Okay, so the essence of all of this is so that you as a chemistry student, you are able to know um how the amount of something can give you the amount of another thing. Okay, it's just like someone who bakes. For example, I like to use this example. Someone who bakes and you know, or even someone who is a chef, you know that you know that you would need a spoon of salt, a full teaspoon of salt, for example, to cook 5 cups of rice. And so, if you're making 10 cups of rice, you would know that you're going to be making use of 2 spoons full, right? And the more you are increasing or decreasing the amount of rice you are making, the more you're increasing or decreasing the amount of um, salt you would be using. So it's the same thing that happens here. That mathematical relationship, that numeric relationship between a particular substance and another substance. That's what stoichiometry tells us. Okay, and it makes use of different variables or different quantities. For example, moles. It makes use of mass. Also makes use of volume. Makes use of Avogadro's number. There are different quantities that one can calculate for when we are solving problems on stoichiometry. Okay, so now that tells us that stoichiometry is not a only a read and understand subject, it's also a calculation subject. Okay, and in every stoichiometric process, one very important thing, one in fact the constant first step is a balanced chemical equation. So we cannot succeed in stoichiometry if we cannot balance um equations. Okay, so one, you have to know how to balance your equations. You have to know what mass is, how to identify the mass in a question, how to identify number of moles, how to convert mass to number of moles, what formula you're going to use. These are the things you have to know. Okay, and you have to know how to identify mole ratio. Okay, mole ratio, for example, we have A, plus B to give us C plus D again, right? So we can say 2 moles of A plus B to give us C and 3 moles of D. For example, now A, B, C, and D can be anything. It could be water, it could be acid, it could be base, it could be one salt, it could be an ion, anything. All right. So this implies that the ratio of A to B is 2 ratio 1. It implies that the ratio of A to C is 2 ratio 1 as well. The ratio of A to D is 2 ratio 3. So that's what ratio is. It's that's what it does. So how do we know what the ratio number is? Just the coefficient. That is the mole, what will represent the mole of each of the substances. Okay, so we can relate anyone. We can relate B to C, whichever substance that participates in the reaction. So if we know the ratio, it means we know the basics. That means, what does this ratio tell us? It means that um for every D, or rather let's say for every C produced, okay, we require 2 amounts of A. For every D, or for every 3D produced, we require 2 amounts of A. So when we are having that, because that is assuming that this whole thing is a balanced equation, okay, it has to be balanced. So that is to say, if we are making use of these parameters A, B, C, and D, okay, we should ensure that the ratios are correct. So if we are making use of A to produce D, all right, we cannot say one A, okay, one amount of A would be used to produce 3 amounts of D. That will be inaccurate because that's not what the balanced equation tells us. So the balanced equation, the ratio we get from the balanced equation will be our standard. All right. And it also implies that every 2 A's will be required to react with 1 B's. Okay. Rather, let me use chemistry terms. Every 2 moles of A, okay, will be required to react with 1 mole of B. So when you are now reacting it with 2 moles of B, you are doing too much and you are carrying out a chemically wrong process. All right, so that's the importance of balanced equations. Now, another thing we can take note of in order to understand stoichiometry is relating this number of moles as well to volume, also, or rather, especially calculating gas volume. You know that standard volume, right, is 22.4. We'll get to that. Now, also to be able to solve concentration. So I've mentioned quite a number of things: moles, mass, volume, concentration. To identify the concentration in a question, what's the unit of concentration? Okay, you know that, and then you know what your question is giving you and asking you to get. What's the unit for concentration? Now I'm asking. If you see a question, how do you know that the concentration has been given? Melody and Rina. Yes, mole per dm cube. That's one of the units. So it can be regarded as the standard unit. Concentration can also be in gram per dm cube. Okay. Now we should also stoichiometry also entails empirical and molecular formulas, how to determine this, right? Molar mass also, knowledge of it, and also Avogadro's number. and also percentage yield and the rest. Okay. So now uh, let me give you some formulas that you have to understand or take note of if you want to solve questions on stoichiometry. So if you are solving things on stoichiometry that often are not things like determining empirical or molecular formulas, okay, you would be requiring these formulas. Okay, we have the mole formula. The mole formula is given as mass divided by molar mass. Okay, and so the unit for mole is mole, and the unit for mass, excuse me, the unit for mass is kilogram. It can also be gram, but kilogram is the standard unit. And then molar mass is kilogram per mole. And so when kilogram kicks out kilogram, we just have the mole. And that's why the unit for mole is um mole. So the short form of writing this is N equals to small m divided by capital M. Another key formula, I hope you both, or you all, are jotting down. Another is we have the mass formula. We can derive it from this mole formula. So if mole is mass divided by molar mass, mass will now be mole times molar mass. And then we cross multiply, right? So no need to write that. And then gas volume at STP, that is standard temperature and pressure. So you can see questions where they say um, at STP, the number of mole for this is equal to what, So that is to say at STP, okay, 1 mole of any gas occupies 22.4 dm cube. Now this is the volume of gas at 1 mole, okay, for 1 mole. So this is like a basic ratio. So 1 mole is equivalent to 22.4 dm cube in volume. All right. And so we have the formula mole. Moles is equals to gas volume divided by the standard 22.4. And so the volume of a gas can now be equal to number of moles, which is small n, divided by 22.4. Not divided by, sorry, times 22.4. Number of moles times 22.4, okay? Now we also have another formula like we also have concentration formula. Okay, concentration formula is given that concentration. Uh-oh. Concentration is equals to moles, which is number of moles divided by volume. Okay, and so we can get number of moles to be equal to C times V, concentration times volume. And then if we are dealing with percentage yield, okay, so percentage yield can be given as actual yield divided by theoretical yield times 100. Okay, and then let's say molecular formula, when we've gotten our empirical formula, we can say our moles. Okay, our number of molecule is equal to our molar mass divided by empirical formula. So we can use this to get molecular formula. And then relative density, okay, that's also another formula. Relative density is equal to molar mass divided by 2 of gas. And then I think lastly, Avogadro's number. Okay. Avogadro's number says every 1 mole of a substance involves or has 6.02 times 10 to the power of 23 particles. Particles can be anything. Could be atoms, could be the molecules, could be, okay, so it could be any. It could be, it's just what that 1 mole contain. Now, this is also like a reference point. Okay, so if 1 mole involves these particles, okay, how many will 2 moles involve or less? So that's like a relationship um, formula kind of. And then we have also again number of mole, Avogadro's number times divided by 2 times 10 to the power 23 particles. All right, so these are the formulas that we can take note of to be able to answer questions in this field. Melody and Rina, are you both still here with me? Now we have a basic and a simple question here on the screen. It says how many moles are of nitrogen? How many moles of nitrogen are there in 2.8 gram of nitrogen gas? Okay, when we say nitrogen gas, we mean the diatomic nitrogen. Okay, nitrogen in nature. All right, there are 7 diatomic elements. All right, we have them from all the halogens up to hydrogen, nitrogen, oxygen, hydrogen at this other end. So all of these are diatomic. So when they say hydrogen gas, we mean H2, not just H. When we say oxygen gas, we mean O2, not just oxygen. When we say nitrogen gas, when we say fluorine gas, say, or molecule, if you call it nitrogen molecule, hydrogen molecule, oxygen molecule, we are meaning O2, not just the element. Now we are implying it in their natural state, which is their diatomic state. All right. So now they said in how many moles are there in 2.8 grams. So when we see questions like this, don't think too far or too serious, right? So the first thing that should come to your mind, if it's a question that um, we are not being told that one thing is reacting with another to give us another thing, okay, then the first thing that should come to our, if that was the case, we'll do a balanced equation, right? But if that's not the case, the first thing that should come to our mind is, what formula can I use to get this? And then we put down all our parameters, all the informations that have been given to us. Now we read it step by step. They said how many moles. That means we are looking for moles, which is n, small n. You take notes, you remember all the formulas that you should know for this. Okay, are there in 2.8 gram of nitrogen gas. Now you're giving mass to be 2.8 gram, okay, of nitrogen gas. That is to say N2. So this mass is for N2. And we're looking for the number of mole of N2 as well, right? Okay. So we should know that if we're being given just mass and N, how to find N, how on earth do we find it? So there is always another variable that they will not be spelled out to you in the question, but it is there. Sometimes it might not even be there. But you as a chemistry learner, okay, you as your examiner would just assume that you should know that there is that information there. Okay, what's the information? Is the molar mass. It might not always be given to you, but you should know that it exists, and it is something that will always come up. It can naturally come up to save a question. So in a question like this, assuming we didn't have all of these in this bracket, right? The question can just end with this question mark. We should know when we write our okay, we don't know number of mole, and then we know mass is equal to this, then we should know, even without being told, that molar mass of nitrogen is equals to 14. So there's elements we should normally know their molar mass without being told. All right, like nitrogen, oxygen, hydrogen. At least the first 20 elements, they are not difficult. Okay, but they are common ones, right? Like chlorine also, sulfur, oxygen, I said that, nitrogen. So actually, the more you are practicing, the more you see more questions, the more you see this number of moles, sorry, molar mass, right? So that of nitrogen is 14, but this 14 is for nitrogen atom, not nitrogen gas, right? So since nitrogen gas is diatomic, we're multiplying by 2 to give us 28. And so remember we said number of mole is equal to mass divided by molar mass. So we say 2.8 divided by 28. Now these are like the beginning, the basics of stoichiometry questions, all right? Now this is what I was talking about when I was talking about mole ratio. Okay, now this is a chemical equation. When we are answering any question that has to do with mass, volume, moles relationship, we some of the times we need a balanced chemical equation. And so in this one, for example, when you see an equation, don't rush into it. First thing, to check if it is balanced. Not all the time it would be balanced, because once it's not balanced, everything you are doing is just a waste. Okay, so this one, when we look at it, it is balanced, right? So since it is balanced, we're going to determine the moles. Now, 2 for this whole substance, 1 mole for this whole oxygen, and 2 mole for this whole substance again. And that is why this is the mole ratio. So if you are being asked how many moles, now I'm asking the winner, how many moles of carbon, or rather, let me say, how many moles of oxygen is required to produce 4 moles of carbon dioxide? Carbon dioxide, yes. Yes, winner. How many moles of oxygen is required to produce 4 moles of carbon dioxide? We have been given the standard ratio on the screen. So anything we are doing other than this standard ratio, we have to do some calculation. We'll have to relate it to this standard ratio based on the balanced equation. So we are not deviating from this balanced equation at the end of the day. So Winner, I'm waiting for your answer.
Okay.
They said no. I said how many moles of oxygen is required to produce 4 moles of carbon dioxide. Yes, Winner. If Melody, if you know the answer, you can also tell us. Based on this
2 moles.
balanced equation, 2 moles. That is it. Okay. So what if we now have the number of mole, okay, of CO2? Or what if we now ask that how many moles of oxygen, or rather, how many moles of CO2 is required, or rather is formed, not is required, is formed from oxygen gas, from 0.5 mole of oxygen. Did you get the question? Okay, I'm going to repeat it. I said, what if you're being asked how many moles of CO2 is formed from 0.5 mole of oxygen? So here again, we're still going to use a balanced equation. Let me properly write this again.
1 mole.
Who was answering? Is it the winner that just joined?
No, it's Melody.
How many moles of CO2 is formed from 0.5 mole of oxygen? It's 1 mole, right? That is it because we are following the relationship. Okay. So that is the stoichiometry in terms of mole ratio. So we can, as we are relating mole ratio, we can also relate their molar mass. Okay. So if 1 mole of um oxygen gas is required to form 2 moles of carbon dioxide, it implies that you know that the molar mass of this oxygen, this O2 now, 16 times 2, which is 32, right? That's the molar mass. And that of CO2, we're not adding the coefficient when we are looking for the molar mass. We're just following the formula. The formula here is CO2, not 2CO2. Now, that of CO2 is we have 12 plus 32, which is 48, right? Wait, 32 plus 12. That is 44, please. So we have 44. It means that we require this 44 is equivalent to this 32, right? It will that's just how it is. We need 32 amount of oxygen to give us 44, which is representing CO2. So it means no, that's not it. That is the molar mass alone, right? But since from the balance equation we have 1 mole of this O32 to give us 2 mole of this O42, so it means that it's more like saying this one multiplied by 32 and then 2 multiplied by 44. Okay, so in essence, 1 mole, one, or rather, in essence, 32 grams. The grams is coming from the molar mass now. It's equivalent to 88 grams of CO2 because we are following the balanced chemical equation. So the mole ratio helps us to relate mass, molar mass, okay, and helps us to also relate to know number of moles. So let's answer a few questions. This is a previous WIEC question. Now, this first question at the top, I want the both of you to attempt it and tell me the answer. I want you to attempt it, Winner and Melody. I believe you both already have um, a pen and a book with you. You're not just listening to me, you're also writing or jotting down. So you can attempt this. The two of you, are you attempting it? Melody and Winner, I need a response from the both of you.
I'm coming, ma.
All right. Now, I just wanted to know if you are trying out the question, if you are attempting it, because I'm expecting answer. I'm expecting an answer based on your solving. If at any point you don't know what to do next, you can also draw my attention. Has anyone gotten the answer? Oh, Winner, you said you did not see my screen. Winner, can you see my screen now? Ah, you still can't see my screen. Melody, can you see my screen?
Yes, ma.
No, Winner, I think your network is disturbing you. Okay, so Melody, have you gotten the answer? Maybe you could try logging in again, Winner, or you have recourse to the recording. Melody, have you gotten the answer? All right, so let's solve it together. Now we have the reaction as we can see below, right? We have sodium tricarbonate reacting with magnesium chloride to give us to give us 2 sodium chloride plus magnesium tricarbonate. Now we first ask ourselves, is this equation balanced? Sodium is balanced, magnesium is balanced, carbonate is balanced, and chlorine is balanced. So this is a balanced equation and we can work with it. Now the question is we should calculate the mass. Okay. So a way to do this, we can you can see from the question, we are dealing with the relationship between sodium tricarbonate 4 and magnesium tricarbonate. These are the two things we should focus on. So it's more like we are kind of going to ignore sodium chloride and magnesium chloride because our center of focus is sodium tricarbonate 1 and magnesium tricarbonate, and their ratio is a 1:1. So we require 1 mole of sodium tricarbonate to give us 1 mole of magnesium tricarbonate. All right, so now we would have this side to be for sodium tricarbonate, okay, and then we have this side to be for magnesium tricarbonate. Now we said we should calculate they said we should calculate the mass of sodium tricarbonate. So the mass we don't know, right? Needed to produce, but the mass of this one we do know, it's 3.36 gram. Okay. And then we're giving in brackets C is equal to this is equal to this, that's equal to that. Those are the what information does that give us? The information that gives us is molar mass. So from here, we can know that our molar mass of sodium tricarbonate, which is the capital M, is equal to sodium is something is blocking my screen. Now sodium is 23, so it's 23 plus another 23 plus carbon, which is 12 plus oxygen 16 times 3. So when we add all this together, someone can add it up for us. So we have 23 plus 23 plus. So we have 106. And then for magnesium tricarbonate, magnesium, the molar mass for one magnesium is 24. So we have 24 plus 12 plus 16 times 3. That gives us 84. Now this is our molar mass. Okay. There are actually two ways we can solve this, but in order to avoid confusion, let's do it this way. This here gives us our molar mass, which is in gram per mole, and this is also in gram per mole. And we remember that for us to get our mass, right, mass is equals to number of mole times molar mass based on that formula I gave you earlier, right? So we know our molar mass, but we don't know the number of mole. This coefficient is what we can relate to know our number of mole. But for magnesium tricarbonate, we know our mass, okay? But then our number of moles, we can get our number of moles from here, which is 3.36 divided by 84. So 3.36 divided by 84, this gives us a 0.04 mole. All right. So now then we'll go back to our mole ratio. Since we've gotten the mole of the other one, we'll go back to our mole ratio and we'll see that in our mole ratio, one sodium tricarbonate gives us one magnesium tricarbonate. So we will relate it to our molar mass. So if one gives us one, then 0.04 will give us how many? It will give us the same thing. It will also give us 0.04. So that is to say the number of mole N for sodium tricarbonate is also 0.04 based on our relationship in our mole ratio, right? So our mass is now equal to 0.04 times 106, which is our molar mass. And then when we will calculate this 106, we have 4.24 grams, right? So this is our answer. Is anyone confused? All right, okay. If you have a question, we could keep it for the next class. And you can also let me know, maybe in the group chat, let me know the topic you want us to learn in the next class, okay? So have you all learned something today? Melody winner and Golden who came at the last minute. Did you learn something today?
Yes, ma'am.
All right.